Okay, we're going to look at motion with constant acceleration. This motion with constant acceleration will be looking at equations. So, first equation is right here. Final velocity is equal to initial velocity plus AT. As you read the points there, you can see where it comes from. We would call this equation 1 when we look at kinematics. What's missing from this equation is position. So if we were to graph this as final velocity being y, initial velocity being my y-intercept, acceleration being my slope, and then time being my x, it's in y equals mx plus b format, or slope-intercept form. So we can use that information graphically. So let's take a look at this and how it would work. All right, so we have an initial velocity of 8.2 meters per second. Our acceleration is downward, negative 9.81. Since we're throwing it up and that's positive, gravity pulls us down, it's going to be negative. What's the velocity of the ball? So final velocity after time is 1.5 seconds. Final velocity equals initial velocity plus AT. My final velocity, I don't know. Initial velocity, 8.2, plus my acceleration of negative 9.81, multiplied by my time of 1.5. I should be able to find my final velocity. So negative 9.81 times 1.5 plus 8.2, and I get negative 6.5 meters per second. Now, negative velocity means that the ball has went up to the peak and is on its way back down at a velocity of 6.5 meters per second. Motion with constant acceleration. When acceleration is constant, the average velocity is equal to the sum of the initial and final velocities divided by 2. So if we know initial and final velocity, and we know our acceleration is constant, okay, we can find the average velocity, which is useful from time to time. Here's an equation where we could use with position and average velocity. So final position is equal to initial position plus final position, initial position plus average velocity multiplied by time. We graphed it just like we do on the graph right there in slope-intercept form. To substitute then some of that into here, final position plus initial position is equal to 1/2 VI plus VF multiplied by T. So once again, if we don't know the acceleration, we can use this equation as long as we know our two velocities. So here, a boat moves slowly inside a marina with a constant speed of 1.50 meters per second. So there's our boat going slowly. Now it's leaving the marina and it starts to speed up. Okay, we know that our speed at the point we leave the marina is 1.50, so that's our initial velocity. We know our acceleration once we leave the marina is 2.40. Since we're speeding up, they're both going to be in the positive direction. And we want to find final velocity after 5 seconds. So we know acceleration, we know initial velocity, we know time, we know final velocity. So let's look back. Okay. And we look here, and we don't say anything with acceleration, so what can we do to help solve for that? Well, remember, we know this equation. Okay, we know initial and final. We can use acceleration to find anything else we need. We can find our final velocity. I'm going to give you another equation that's going to come up, and it's the final position, but we got final velocity, and that's going to be initial velocity plus AT. Our initial velocity is 1.5 plus our acceleration of 2.4 multiplied by our time of 5 seconds. Our final velocity, and again, I'm not going to do all the math for you, but our final velocity will be 13.5 meters per second. So our boat will be going 13.5 meters per second at this point after it leaves the marina. So the question is, how far does the boat travel during this time? Let's look back. We know our two velocities and time, so we can find our final position to help solve for this. Okay? So xf plus xi plus, when you look back here, 1/2, because that's what we're finding an average, 1/2 v final minus vi times t. Our initial position right here, we'll say, is 0. 1/2, so our final velocity is 13.5 minus our initial velocity of 1.5 multiplied by our time of 5 seconds. And when we do all this math, what we come out to find is we get 0.5 multiplied by 13.5 minus 1.5 times 5, and our distance is 30 meters. So we have traveled 30 meters during that 5-second time frame. I'm sorry, not 30 meters. If I could do my math better. 37.5 meters during that time frame. Now, let's take a look at what we know from this, okay? We got a velocity time curve here, and we want to find distance. Now, our slope of this tells us our acceleration, and we can find acceleration finding the slope between these 2 points. But the area under the curve, so if we can find the area under this curve, we can then find the distance traveled. So we break the area under the curve up into a triangle, which is this. The area of a triangle is 30. Then we got the rectangle. And when we want to find the area of the rectangle, it turned out to be 7.5 base times height. We add those two together. There's our 37.5 meters, and we have solved for our distance traveled. So graphically, we can do that, area under the curve. And again, you can follow this direction here. That equation can be combined with the other. The first two equations can be, and we can get this, where final position is equal to initial position plus initial velocity times time plus 1/2 acceleration times time squared. This is probably the most useful equation, even though sometimes if you're solving for t, you can get a quadratic. And then let's say we accelerate, but we do not know the time during this, and this is another important one without time, because we can find something missing without knowing time. If we know initial and final velocity, acceleration, and position are 3 of those 4, we can get this. We can solve for the other without knowing time. So drag racer starts from rest, accelerates 7.4 meters per second squared. How far will it travel in 1, 2, and 3 seconds? So we start from rest, which means our initial velocity is 0. Our final velocity is unknown. Our acceleration is 7.40 meters per second squared. And then our time is going to be 1 second or 2 second or 3 second, right? So final velocity we don't know. What we're looking for is our final position. Our initial position in this case, since we're traveling this way, will be 0. Our final position, unknown. So final position is equal to initial position plus velocity times time plus 1/2 a t squared. This is 0 and this is 0, so our final position is going to be 1/2 a t squared. 1/2 times our acceleration of 7.4 times our time, in this case 1 second squared. So for 1 second, our distance traveled will be half of 7.4. 3.7 meters. So let's take the second. So we take 3.7 times 4, because that's 2 squared. And after 2 seconds, we're at 14.8 meters. Now let's take it one step further and multiply it by 9, which is 3 squared. So after 3 seconds, we will have traveled 33.3 meters. And you can see that our distance apart really progresses as we accelerate, which it should. So here are our equations, and I'm going to tell you that most of the time, these big 3 are the 3 you'll use. Keep the other 2 in your toolbox because you'll need them. This one Final initial velocity, acceleration, and time. No position. This one has everything but final velocity, and this one does not have time. And so now you can take a look at what you have, but also look at what you don't have in a problem to see if it's beneficial to pick your equation. So let's see, a park ranger driving on a backcountry road sees a deer frozen in the headlights 20 meters ahead. The ranger is driving at 11.4 meters per second, immediately applies the brakes, and slows an acceleration of 3.8 meters per second squared. How much distance is required for the ranger's vehicle to come to rest? A lot of information there. Let's take a look. Initial velocity, 11.4 meters per second. Sorry, initial velocity. Initial position is 0, because we're going to start from where we're at. Even though it's 20 meters ahead, we're going to pay initial position 0. Final position, we're going to solve for. We know our acceleration is 3.8, but it's going to be a negative acceleration because if we're traveling this way, 11.4, and we slow down, our acceleration has to go opposite. So it's negative 3.8. And then our final velocity should be 0 because we're going to come to a stop, right? So we know we're trying to find final position. What are we missing? We're missing time. So right away, final velocity squared, initial velocity squared, plus 2a times my change in position. So I'm going to go with this equation right here because we don't know time. My final velocity is 0. My initial is 11.4 all squared. 2 times negative 3.8. And then we're going to get our change in position from there. Okay. So 11.4 squared divided by 2 times 3.8 gives me a change in position of 17.1 meters, which means by applying the brakes, I will travel 17.1 meters. The deer's 20 meters ahead. The park ranger will not hit the deer and we'll all be saved. Let's look at a graph of this situation. So here's our initial velocity. Okay, and you can see that we will stop short of the deer, which is good because now the park ranger's car is fine, the deer is fine, everybody's fine.